In this video, I would like to discuss two properties of sampling distribution. To understand the first property better, let's have a look at the example. So suppose two statistics, some A and B, exist to estimate the same population parameter theta. So we've got two sample statistics A and B, and both of them estimate some population parameter theta. And suppose those two statistics have sampling distributions as shown below. On the basis of these sampling distributions, which statistic is more attractive as an estimator of theta? So let's have a look at the graph on the left. In this case, we can see that the mean value of the sampling distribution of A is the same as parameter theta, so both of them are in the middle of the distribution. However, if you look at the graph on the right, you can see that the mean value of the sampling distribution of B is in the middle as it should be. However, the true population parameter is to the left of the mean of the sampling distribution. And the difference between the two is called the so-called bias. Since in the first case, in case of the first graph that we have on the left, the mean of a sampling distribution is equal to the population parameter, it is said, so A is said to be an unbiased sample statistics for the parameter theta. However, as we can see in the graph on the right, the mean of a sampling distribution is different from the population parameter theta, and there is a bias between them. So we say that B is a biased sample statistic for the parameter theta. Therefore, if the mean of the sampling distribution is equal to the parameter it is intended to estimate, a statistic is said unbiased, which is good. And if the mean of the sampling distribution is different from the parameter it is intended to estimate, a statistic is said to be biased. So we want our statistic to be unbiased because we want the information that we get from a sample to be representative of the population. So we want a sample statistic to be as close as possible to the true population parameter. And when they're equal to each other, this statistic is said to be unbiased. So we get the most realistic representation of the population. And to understand the second property better, let's have a look at another example. So once again, suppose two statistics A and B are both unbiased estimators of the population parameter, so their sample means are equal to the population means. Since the means of the two sampling distributions are the same, we turn to the standard deviations in order to decide which will provide estimates that fall closer to the unknown population parameter. So if you look at this graph, you can see that the sampling distribution for statistic A is closer to the true population parameter. It's closer to the middle of the distribution, to the mean of the distribution, whereas if you look at the sampling distribution for statistic B, you can see that the values are more spread out around the axis. So the values are further away from the true population parameter or from the mean value. And since we would like to get as close as possible to the true population parameter, we would like this spread to be as small as possible. So in this case, a sampling distribution for statistic A is a better representation of the population parameter. So in conclusion, smallest standard deviation means that the values of the sampling distribution are closer to the unknown population parameter, which is better for us. That means that the sample statistic that we have is a good representation of the unknown population parameter. And on the other hand, largest standard deviation means that the values of the sampling distribution are further away from the unknown population parameter, which is worse for us because that means that the sample statistic that we've got is not a very precise representation of the unknown population parameter.